So today we're just going to have a recitation session. And we'll be talking about just a few things, so it shouldn't take too long, actually. The first thing I wanted to just briefly mention was, so homework 2 and lab 2, we're almost done grading those. Homework 2 we'll be going over in a little bit, but it was a really long assignment, as I'm sure you now realize. Right, so we're almost done with that. Lab 2 is being graded. Looks like people tended to do fairly well, similar to the first lab also. So we'll be getting those back to you soon. And I'll be talking about the grades and distribution on Monday, okay? Right, feedback. So I'm sure many of you, hopefully all of you, well maybe not all of you have turned in your feedback forms. If anybody wants to, who hasn't already, fill out the feedback form, I have some up front here. So just let me know, raise your hand, come up afterwards and grab some. But that's really important for us because we can dynamically change things that are going on in the class based on your feedback. So it's really important to let us know, what is the pace of the course like? Is it too fast? Is it too slow? Do you think the lectures are too long? Too short? Probably not. And different things like that. So we want your feedback. It's really important to us. OK, so any general questions before I start? Because today I'm just going to be discussing homework 2. And like the previous recitation session, I'm going to be going over the answers, which are already posted. But I've also gone through and I've sort of annotated them with things that I think might be interesting exam questions, exam style questions. So those are thrown in to add a little bit more to this recitation. But any general questions first? OK, cool. Then let's dive into homework 2. Now, the first question, sort of the infamous question on the LC3B microcode. So lots of people got really good scores on this part of it. And I'm assuming it took a lot of time in order to get those scores. So we went over a couple of those, or Professor Mutlu went over a couple of those instructions, I think 3 in class, and sort of went through what is the flow of how do you figure out what the control signals are at each step of the way. I'm not going to go through all of the control signals because, like you know, it would take a couple of hours at least. But I'd encourage you, if you don't understand where some of these control signals are coming from on the solutions, talk with the TAs in office hours, talk with the TAs in labs. We'd be happy to explain them to you, OK? So if you have any lingering questions, just feel free to go to office hours to chat. OK, so the next question so the first, I guess, not huge microcode question was looking at data reuse. And this was a little bit similar to a question that we had on the first homework, if you remember. We asked you to look at different number address, like the 1 address, 0 address, 3 address, ISAs, and sort of compare how do they compare in terms of code size, in terms of amount of data transferred. So this is going into a little bit more detail on a couple of those. So in this question, we have 2 different machines, machine X, machine Y. Machine X is basically a 3-address memory-to-memory machine. Machine Y is a 3-address load-store machine. And they have a few different details going on about them. But we asked you to take these 2 machines and 2 different programs and compare how they access memory in terms of loading instructions and loading data. So I'm just going to quickly go through that, and then we'll talk a little bit about that. OK, so first, let's take a look at the high-level program that the programs that we'll be dealing with here. Let's look at program A. This is for question 2. OK, so it's fairly simple. A equals A plus 1. B equals B plus 2. And so on. OK. So that's the first program. And if we look at how this program would be implemented, or how it would be performed on a 3-address memory-to-memory machine, it's pretty straightforward, right? I mean, we have memory addresses. We have spaces in our instruction to specify memory addresses that we want to perform computation on. And so the translation is pretty straightforward. We could do something like, so this is for machine X. We could just translate it as add a, store into A the value A plus 1, and so on. Store into B the value at B plus 2. Store into C the value of C at C plus 3. And the same for D. OK, that's pretty straightforward. So life with a 3-address memory-to-memory machine is really nice for the programmer. What about the load-store architecture? So machine Y. OK, well, things get a little bit more complicated now, right? Because now we can't directly operate on memory addresses. We need to actually bring the contents of memory into the register file, work on it from there, and store it back to memory at the end of the day. So what we're going to start to see is we're going to see a bunch of loads and stores being added into the code. So it looks something like, first thing we need to do before we can even perform some computation is just load the value of A somewhere, so we have it lying around. So maybe we choose to load into R1 the value at memory location A. And now that we have the value of A loaded into the register file, now we can start operating on it. So we could, for example, add 1 to this register, and that basically performs this operation. And when we're done with that, we can store the contents of this register back into memory at the location where it was before. OK, and you can imagine repeating this procedure for the other instructions that are here, right? OK. Now, after you wrote these code segments, what we asked you to do was figure out how much data was transferred when running each of these programs on the different systems. And I think it's useful to sort of break the how much data was transferred number into how much data was transferred in terms of instructions and how much data was transferred in terms of actual bits of useful data from memory. So let's take a look here. If we look at machine X, we're going to have some amount of bytes that are moving around the system attributed to code, and some amounts that are attributed to just the raw data. OK. So in terms of code, it's relatively simple. We specified that in this machine, each of the instructions was 4 bytes in length. So that's pretty straightforward, right? So for, let's label them instruction 1, 2, 3, 4. 1, 2, 3, 4. For each of these instructions, we're basically just transferring 4 bytes, right? 4, 4, 4, 4. OK, great. Now, in terms of data, here's the thing. Each time we execute one of these instructions, what do we have to do? We have to load the data from that memory address and then store the data back into the same location, because we're just dealing with memory addresses, and we need to preserve the data that's stored there. OK, so if we look at what's happening in machine X, we have something like this. So if this is memory, and we have an instruction like this, add 1 to A, and store it in A, the first thing we do is we're going to have to basically load some data from A. Look familiar? Load some data from A. That takes 4 bytes. And when we're done with everything, we're going to need to eventually put that back. The machine is going to need to put that back. So we're going to need to store some data back into A. Deja vu, right? So basically what this machine is doing is it's loading and storing, similar to how a load-store architecture might. In this example, as we'll see in the next example, these machines will actually differ in the way that they're moving data around the system. Anyway, in terms of data, for each instruction, we're loading and storing a total of 8 bytes of data. Okay. You can see how that's going on in the system, right? Okay. Okay, so anyway, we have 16 bytes of code. No, we don't have 16 bytes of code because yeah. Well, no, so that's actually, the immediates don't matter so much. But what we specified, for this machine is that each of the instructions takes 7 bytes total. Okay, so just off by a constant. You'll see where I got confused in the second part. But for now, what we have is that each of these instructions actually takes 7 bytes of data. OK, so that's actually 28, 32. OK, and that gives us our grand total, 60. Sorry about that. So OK, this is for the machine where we're basically just doing memory-to-memory computation. Great, things look good. So what about the machine here where we're actually doing loads and stores? What happens in that case? So let's take a look at machine Y. And let's look in terms of code data again. Here are 2 views of the system. Now, if I actually look back to the problem, we'll see that for machine Y, each instruction is encoded in 4 bytes, and the data is the same as the other machine. Each time we transfer data from memory, it's 4 bytes as well. So for machine Y, what this looks like is each of the code segments, and if we call this like 1, 2, 3, ... 1, 2, 3. For each of the instructions, we're loading 4 bytes from memory. And for some of the instructions, like loads and stores, we're actually moving data back and forth between memory again. So for some of these instructions, like instruction 1 is a load, we're going to transfer 4 bytes. Instruction 2, though, is just an add. We're adding some constant value to a register. We're not moving data back and forth between memory, so we don't actually transfer any data there. And then we store that data back, and so on. So we sort of have this oscillating pattern. At the end of the day, this takes 48 bytes, and you can look at this on the solutions. This is 32 for a total of 80. OK, that's fine. That's relatively straightforward to go through and do yourself. So a question, though, is why? Fundamentally, why are these instructions less data? Why are we storing less data in these instructions than these instructions? 7 bytes versus 4 bytes. Where do the 3 bytes go? What's contributing to those 3 bytes? Yeah?
Addresses are much bigger than register numbers.
Address numbers are bigger than register numbers. Yeah, exactly. So with a memory-to-memory machine, remember, we're dealing with addresses. Maybe our addresses are 32 bits. Maybe we can shave off some of those bits if we have some sort of offset, some global offset that we always access data from. But still, we want to be able to access a lot of data. We're going to need a lot of bits to store that information. Registers, on the other hand, as we've seen, they're kind of on the order of 32 registers. That's much fewer potential locations for accessing data than a huge amount of main memory. So fundamentally, that's the trade-off that's going on here. OK. If we look to this machine, though, if we look to the load store machine, what's the primary advantage that's going on here? What's the benefit of using a load store machine versus a memory-to-memory machine? And you can answer it in one word. So this is one of those things where on the exam we might say, what's the primary benefit of a load store architecture versus a memory-to-memory architecture? Please answer this question in one word. Yeah?
Data reuse.
Data reuse or locality, right? If you use data reuse as an adjective, I guess you could hyphenate it and then it's one word. But yeah. But that's exactly the right concept. Data reuse, locality. Basically, the register file lets you store temporary data that you're going to use within a short amount of time. It's very frequently used, hopefully, so that you benefit from having this structure here. Which brings me to the next question. What are the disadvantages of this architecture? We kind of touched on it in the last recitation session. Do you remember when we talked about a machine that has a register file, what doesn't come for free compared to, say, a memory-to-memory machine? Yeah?
Well, one of the obvious ones is code size. I don't think that's what you're talking about.
So code size could be larger, right? So as we'll see in the next example, if you have a lot of reuse, then maybe it can be similar to a memory-to-memory machine. That's good. So that's sort of a software side of things. What about on the hardware side? What if you're actually building this in a chip? What are you considering as you're designing this processor? What if I told you that I'm the CEO of your chip company, and I say, every register you add costs us another however many thousands of man hours to verify, however many tens of thousands of dollars to tape out for our prototypes, costs 4 watts in terms of energy or in terms of power. Are you going to be careful about how many registers you add to your machine? Probably. Probably. You're going to want to pick a number that is suitable for your purposes. So anyway, getting back to the question, for a load store machine, we have this big register file that we need to actually add to the architecture. And that's expensive, potentially. OK. So this was for program A. I'm going to quickly go through program B, because I think that you guys understand what's going on here. But I just want to lay it out so that I can set the groundwork for some of the questions that we can discuss. OK. Still question 2. So if we look at program B, what's going on here? In the load, or in the memory-to-memory machine, well, let's go back here. Let's write down the program. Program B is doing something a little bit more interesting. It's not just adding a constant number to each of the addresses in memory. It's actually adding multiple addresses in memory together. So for program B, what we're doing is B equals B plus A, C equals B plus A, reuse. We'll come back to that. A equals B minus C, D equals B minus C. OK. And for machine X, what do we have? Let's take a look. So still, this is still good for a memory-to-memory machine, right? Arguably, it's even more convenient in a memory-to-memory machine because we have our full 3 memory addresses. We can utilize the power of a memory-to-memory machine to its fullest now. So we can do something like add, store into address B, the value at address B plus the value at address A. Same thing, add, store into C, the value at B plus the value at A. Subtract.
Those bottom 2 might be right. Maybe A minus C.
Let me take a look. Yes, you're right. It is A minus C, so we don't have that. Thank you. Thanks, Dylan. Devin. A minus C. OK, that looks better. Thank you. So right, so for the memory-to-memory machine, we can just go through here, subtract, store into A, value at B minus C, and same thing, subtract store into D, value at A minus value at C. OK, that's pretty straightforward. What does it look like for machine Y? OK, here's where things start to get interesting, and where we wanted you to hopefully pick up on, really drive home the distinction between these different types of machines. As you can already guess, in this particular program, we're reusing values quite a bit, right? B is read 3 times here. It's modified here, used again. A is used a few times. C is reused. OK, so you're starting to see how by adding a register file to this system, we can potentially reduce the amount of data that's moved between memory. And we'll see this right now. So what you can basically do for the load store architecture is you can load the values that, basically the values that you're going to be reusing into the register file and just keep sourcing them from there. So in the solutions we gave, we loaded into R1 the value at A. We loaded into R2 the value at B. And what did we do now? We can just kick off the computation and start going. So B is in R2, so we want to eventually store the result of our addition in R2, and we want to add the value in R2 to the value in R1, store that in R2. OK, good. Basically do that again for C, right? Where is C going to reside? Actually, in the solutions we gave you, what we did was, because we want to reuse this value of B right here, or we might want to reuse the value of B, what we did was we actually stored this in another register, R3. So this sort of stores the updated, this stores the sum of B plus A. OK, so then we can once again go through and add these stored in R4, the value R3, which is the updated value of B. That's the one we want to use here. More on this in a second when we talk about dependencies. And we add that to R1, and so on. And at the end, what do we do? Because we specified that everything needs to go back into memory again, we just store the contents of the registers back. So we store R3 at B. We store R4 at C, R5 at A, R6 at D. OK. I'm not going to go through the code and data portions on this program in a lot of detail, but I just want to point out that now what you'll find is that whereas this machine is still transferring a lot of data in between main memory. In fact, it transfers even more data now because we're using 3 memory addresses per instruction. This machine can actually save a lot in terms of data transferred from the processor to memory, because a lot of the operations are going on in the register file. Why is that important? Why does it even matter that we don't transfer some data from the processor to memory? Deb? Accessing the register files fast. Faster than main memory, by orders of magnitude, really. That's one reason. Also, memory bandwidth isn't unlimited. Maybe we have like a superscalar architecture, which we'll talk about. We've already started talking about. Maybe we have an out-of-order machine where you could potentially have hundreds of instructions in flight. Your memory bandwidth on your system might not be able to handle hundreds of simultaneous loads and stores. So that's another key constraint when designing systems is memory, which in fact we'll start talking about probably soon. We'll go over some virtual memory concepts next week. Memory is actually a very critical bottleneck, even in existing systems today. It's interesting because years ago, when processors, when some of the first systems started being developed, the speed of memory, or just storage, was actually similar to the speed of the processor itself. And for a while, the speeds of those two components kind of scaled nicely with one another. One wasn't typically faster than the other. So if you accessed memory, it took you about the same time as performing an operation in the processor. What happened, and what the trend continues to be today, is that the speed at which you can access memory is still increasing, but at a much, much slower rate than the speed that processors are improving at. So if you look at over time, and let's just call this speed. I'm not going to go into a lot of depth here. But if you look at this and we have like, let's say this is processors, this is memory. Way back at the beginning of time, like in the 1940s, when computers started being developed, what you had was that processors and memory were kind of relatively similar in terms of speed. And recently what we've seen is that processors have been getting increasingly faster. This is just due to a lot of device type things that are going on in how we fabricate these technologies, how we can scale the transistors down further and further. But memory technologies really haven't been improving by as much. And in fact, as time goes on, that gap, what some people call the memory wall, but that gap really is getting larger and larger. So that's a really important constraint. Anyway, huge aside there. I think that's interesting to note. We'll get back to that when we start to talk about main memory. OK, so for a second, though, while this is on the board, let's talk about dependencies, because there's definitely going to be some questions about those on the exam. Let's go to another aside, actually, on the exam. Professor Mutlu likes to offer questions on the exams that sometimes require some reverse engineering. So looking at the current state of a system and inferring what some initial state was, or basically figuring out what the next state will be. So for example, we might give you the contents of a register file, the contents of a pipeline, and say what were the instructions that were executed on this system in the last 5 cycles. So you really this is going back to the previous recitation. You really have to be familiar with this material and really know what's going on in the system so that you can look at that type of question, figure out exactly what's going on, and start to trace back, OK, what were the steps that led to this current state in the system? But let's talk about dependencies for now. So let's start at the beginning, I guess. What are the 3 types of dependencies? Do you remember?
Read after write, write after read, write after write.
Yeah, so let's go through them one by one. Let's start over here. So what Devin mentioned was read after write. Does anybody remember what we kind of colloquially refer to this as?
True dependence.
It's a true dependence, yeah. We're not going to test you on like vocab terms, by the way. It's helpful to kind of refer to them by these other names sometimes. OK, read after write. There's a write after read dependence, which is called, it's actually called an anti-dependence. Talk about these in a sec. And then there's a write after write dependence, which is an output dependence. OK. So how can we get rid of dependencies? What's one way?
Compile.
Elaborate.
Compile. We just figure it out somehow, magically.
When you say figure it out, though, what do you mean?
Use certain registers so that there are no dependencies
Mm.
on the registers. Like if that was possible, I don't know.
So mapping, in this example, maybe mapping the different data values to different registers, kind of like we did right here, right? Because R3, even though our instruction was B plus A equals B, how I started writing it was R2 equals R2 plus R1, B plus A equals B. But what you can also do is you can say B plus A equals some new data value that I'm going to name R3. So that's one way of doing it. Can we get rid of, so what type of dependencies can we get rid of using that compiler-based technique? Can we eliminate all dependencies? What if I said we had infinite hardware? Your register file is infinite in size. Could we get rid of dependencies ideally?
No.
No? Why not?
A lot of times we have to write, you just need to update a value. Like if you have a certain number of operations that you're doing on the same value, you have to, always is going to depend on the previous operation. So.
Yeah, so even if we had infinite hardware for performing renaming, for shuffling around values in the register file, we could only eliminate these type of dependencies, anti and output dependencies, because these dependencies arise because we just don't have enough registers to hold all the logical values that we want to deal with in our program. So we end up stalling, we end up spilling data. But read after write dependencies, what these really tell you is that I want to read a new value that I generated that I can't read until that value has been computed. Unless we use something like prediction, which we kind of talked about a little bit. Let's not worry about that for now. We can't eliminate those dependencies. That's why they're true dependencies. They're the only dependencies that actually will still exist if we had infinite hardware and compiler resources to modify these programs. Okay? Good. So there were a couple more parts to question 2, but I think that we've covered a lot of the similar concepts that we were asking you about there. So I'm going to go ahead and jump to question 3, which was looking at fixed versus variable length ISAs. So if you remember, a fixed length ISA is where you have an instruction, it's very well defined to be X number of bytes. Every instruction is that number of bytes, and in this slot, there's this information like an opcode. In this range of bytes, there's some maybe a register. In this range of bytes, there's maybe a function code. It's very regular and very simple, in fact. Variable length ISA, not so much. Maybe the first byte tells you how many trailing bytes make up the instruction. And so you need to look ahead, grab those bytes, and interpret them, decode them. I think we were talking about the x86, which I think Professor Mutlu said that the longest variable length instruction was something like 17 bytes. I think I later looked, and it's more like 20 plus bytes now for the longest instruction. So these things can get pretty complex, not just for the compiler, but for the machine to actually decode. But let's take a look at a couple of simple examples of that. So the program that we gave you to translate into these 2 types of ISAs was relatively simple. We just had an add, question 3, R3, R1 plus 2, store in R3, shift left logical, R3 by this amount, move R5, this value into R5, and store a word from R3 in the memory location R5. OK. And once again, we wanted you to take a look at probably what's one of the key trade-offs between these two types of ISAs is how much code is actually read from memory. Remember, that's a key bottleneck. And how long does it take to actually decode these instructions? Because if bandwidth were just a concern, it might just be worth it to have really, really complex long instructions. But there's an additional cost that we have to factor in, which is how do we actually decode what those instructions mean? So let's just quickly go through this. So you have code size here, and we'll call it cycles, which is basically execution cycles that in some cases could be, in some cases decode could contribute a large portion to. And we'll have fixed length, variable length for each of these. OK. So let's look at the question. So what we mentioned was that in terms of size, the opcode and each operand in the fixed length architecture is 1 byte. So there's 1 opcode, 3 operands. That's 4 bytes per instruction. And the register immediate, like add, shift left, instructions take 1 cycle. And the all other instructions take 4 cycles. So that's pretty simple, right? That's a really simple design to implement potentially in your system. So contrast that with the variable length ISA. Here what we have is that each of the instructions, the opcode is 1 byte, and again, each of the register or immediate fields are an additional byte. But remember, we don't have to use all of them. That's the beauty of a variable length ISA. Some of them we'll use, whichever ones we don't need, we won't use. The trade-off, though, is that in this ISA, it takes a lot longer to execute the instructions because there's additional decoding time. So for example, register immediate takes 3 cycles. That's an additional 2 cycles compared to the fixed length ISA, and load store takes 6 cycles. So we've basically added 2 cycles onto the decode phase in order to get this variable length property in our ISA. So what does that end up looking like in terms of code size? Well, for the fixed length ISA, it's simple. Each of these are just 4 bytes, like we just talked about. 1 for the opcode, 3 for the operands. For variable length, the first one is 4 bytes because we actually do need all 4. We do need all 3 of the operands in the instruction. But the rest of the instructions actually don't need that third operand. So they're only 3 bytes each. OK, so variable length ISA is a win in terms of code size, not surprising, because as we just talked about, it's going to be smaller because you don't need to pack everything into the same number of bits. There's no internal fragmentation, if you want to think of it a different way. In terms of the cycle time, though, required to execute these programs, fixed length, remember, for all the register immediate operations, that only takes 1 cycle. So add, shift left logical, move. Storing data back to memory, that takes longer because we're accessing memory, but still it only takes 4 cycles. Is that total? The variable length ISA, we're adding 2 cycles to every instruction. Not just the complex ones, not just the simple ones, to every instruction. So what does that look like? 3 cycles here, 3 cycles, 3 cycles, 6 cycles, for a total of 15. Takes over twice as long to execute than the fixed length ISA. Okay. This is a key trade-off between both of these. Here's a question, though. We told you that variable length ISAs have increased decode complexity. But why? What is it that causes that increased decode complexity? Or where does that complexity arise from? Yeah?
You can no longer just say that the opcode is stored in exactly such and such bytes, or every parameter is exactly where you expect it to be. This could be anywhere.
Yeah, if you think about it, you can't just say, I'm going to grab the next 64 bytes from memory and chop it up into a bunch of instructions, locate the opcodes to each of those instructions, locate the operands to each of those instructions, and make a decision about whether I want to execute these, predict a branch, forward them to some load store unit. You can't do that as easily with a variable length ISA. But in addition to decode complexity, what else is more complex in a variable length ISA? Think about what we've learned about in class so far. We've covered a lot of material, actually, which is good. But in a variable length ISA, can you imagine what else is also complex? What does it make more complex?
Your next PC logic has to be it has to predict a branch on every instruction.
So, right. So, yeah, I like what you're getting at. The next PC logic becomes much more complex because we don't know if this is the start of a branch, if when we branch, where are we going to actually branch to? It's not clear that we're just going to branch. If we say we're going to branch n instructions into the future, what does that mean? Like, we can't compute that value. So yeah, you basically have to start predicting. So here's one way of dealing with this that I'm going to throw out there. In a variable length ISA, if we have instructions whose lengths can be whatever, basically, some are small, some are large, and this is your current instruction that you're trying to decode in your 3 cycles or whatever, 2 cycles, you basically have to say, OK, well, I have no idea if this is a branch. And I'm not going to be able to determine that during this cycle. But I know that branches look like this. And I know that branch target address maybe is here. And I know that, do you see what we're doing? From every program counter, you basically say, I'm going to treat the next branch instruction number of bytes as a branch and try and predict it and see if I have a high confidence for that instruction if it's or those number of bytes if they're interpreted as a branch. That's difficult because now your logic for branch prediction needs to be more complex. You might have a lot of noise in the way that you're determining whether something is taken or not taken. It increases complexity. Good. And what about for, so I'll ask you the question. What about for other types of machines that we've looked at? Can you think of any other downsides of a variable length ISA? This is a single instruction, right? But we've looked at other machines that don't just fetch a single instruction every cycle, right? What about superscalar machines, where you want to be able to say, hey, can you fetch the next 4 instructions so that I can start feeding my functional units? What does it mean to fetch the next 4 instructions in a variable length ISA? Maybe you overfetch and you fetch a bunch of data. Yeah?
Yeah, maybe you just, like you pretended it was a branch, maybe you just pretended all different kinds of instructions.
Yeah, so that's one possible solution. Let's take the next 64 bytes. Let's try all permutations of variable length instructions. Well, actually, I don't even know if that's possible, but it's one potential idea, right? You could do something like that. You could do some approximation and say, I'm going to make some rough guesses as to what instructions are enclosed in these 64 bytes. But now you're adding complexity to your system that wasn't there, that isn't there in a fixed length ISA. OK, good. So, and then there were a couple of questions that kind of were discussions on this topic, which I'm going to skip because we discussed a lot more than that, in fact. So the next question was on addressing modes. Remember, we talked about these in lecture. This is basically, it basically determines how the nature of a memory access. Because we don't always just, in some machines, we don't always just say, I want to access this exact address here. There could be other things that we do. We could say, I want to access this exact address plus this offset, maybe. Maybe I want to scale that by a value. Maybe I want to access the address that's actually stored in a register file entry. So there's different choices here. And they suit, as you can imagine, different programming styles. So I'm just going to go through this relatively quickly. OK, so let's just quickly review what the different addressing modes are. And then we can kind of, you're familiar with, hopefully, with the homework assignment, and we can just go through those relatively quickly. So we gave you a few of them. There's actually more. This isn't a comprehensive list. These are the ones that might be particularly interesting to implement in systems, and which existing systems do implement. So this is question 4, addressing modes. We have absolute, register indirect, based, which is really just base plus some sort of offset, memory indirect, and auto increment decrement. OK, by 1 byte, we said. By 1 byte. OK, so I want you to fill in this table for me. Here are the types of addressing modes. In terms of where the address is stored, so let's say address is stored in ... I want you to sort of look at, I want you to take into account the addressing modes that we've talked about and tell me where is the address stored in an absolute addressing mode. Where do we find the address for a memory operation? We have to get it from somewhere, right? Or is it random? Maybe it's random. No, where does it come from? So in an absolute addressing mode, the address is stored in some place in the instruction itself. We'll typically have some sort of immediate field that says, go to this memory address, access that data. So it's actually stored in the instruction in some sort of field. What about register indirect? Where is the address stored in a register indirect addressing mode? In just some sort of register, right? I mean, I guess that's the idea. We're accessing memory indirectly through an address that's stored in the register file. So it's just stored in a register somewhere. What about based? Where does the base and offset come from? So yeah, here's a case where it's not entirely clear. We could have base and offset stored in registers. That could make sense, where we have some sort of, global memory location that we want to always index relative memory values from. But there's no reason why it has to be stored there. We could store this just as easily in the instruction. But now we're talking about adding one memory address length field to an instruction plus some sort of immediate offset. Maybe it's a mix. Maybe the base is in the register file, but the offset is in an instruction. So basically, this could either be in the instruction, could be in a register. OK. Memory indirect. Where is the target address that we want to access stored in a memory indirect? In
memory.
In memory. Yeah. So it's kind of weird because now we're talking about the hardware performing indirection, kind of like following pointers. But But that's the case here. Basically, we specify a memory address, and we say to the processor, hey, can you load or store from the value, from the memory address that's stored at this memory address. So this is in memory. And auto increment decrement, this is basically just we're looking at the contents of some register, using it to access memory, and then we're modifying its value in some way, in this case in 1 byte, increments. OK, so that's where the address is stored. If we look at the 4 examples, which I'm just going to just highlight very quickly. Basically, the first one was something where we have like 4, and then some sort of like I++, and we're accessing elements at I. You can see how this type of programming style would be amenable to using auto increment decrement, right, by 1 byte. If A is like a uint, what do we say? Uint 8, 1 byte sized. We have some array. So each time we access A, we're going to the next element, and each element is a byte. Yeah?
Do you have an auto increment by another size?
Of course. Yeah. So auto increment doesn't have to be 1 byte. It could be whatever, there could be some sort of field in your instruction, in your auto increment instruction that says, hey, by the way, auto increment by 2 bytes for this instruction, 4 bytes, something like that. But just for the purposes of this question, we defined it as 1 byte. So that was the first part. That was part A. The next one was actually really similar. And the first time when I was going through and doing the homework, it actually tripped me up when I was looking at this, because I didn't notice the subtle difference at first, which was now we're not going through the array in terms of 1 byte increments. Now we're actually going through the array in terms of 4 byte increments, right? Because this is an integer value that we're dealing with. So we have the same for something with I++, AI. So the type of addressing mode that actually works well for these type of access patterns is something like this sort of like, oh, we missed one, didn't we? There's scale. I was like, where is it? There has to be another address type here. Yeah, so there's scale indexed, which is basically just base plus index plus constant, base plus index times constant. And again, like the based address mode, these could be stored in registers. They could be stored in the instruction itself. We have that flexibility here. Right, so for this type of access pattern, we really want to use the scale indexed mode, right? Because we're accessing it at these sort of constant strides, 4 bytes in this case. OK. The next one was looking at if we have some address that's stored in a register, and we want to access the data at that address. So what does that look like? We have a pointer to an integer, p, and we want to access the data at that address, p, and we tell you that the pointer is stored in the register file. So for this type of access pattern, we would want to use something like register indirect, right? Because our pointer is in the register file, and we just need to go to that address and modify the value. OK? Finally, the last one, we said, now we're going to give you a double pointer to p, and we want to access the data at that second level of indirection. But we're still only storing the address of the first level of indirection in the register file. So in this case, what we would want to use is something more like memory indirect. This is stored in the register file, and we can use a memory indirect access to actually perform this address computation and load or store. In this case, I guess we're doing a store. So that's the case, that's the deal with those. So this makes sense, right? OK, good. So one of the modes that we didn't use, actually, was absolute, an absolute addressing mode. What's an example where we would want to use it? Can you give me the code example, or just pseudocode, where we would want to use an absolute memory addressing mode? Yeah?
So it's like if you're just jumping somewhere, so maybe like a switch in case statement.
Switch. Go a little bit more concrete.
If like, so if you have like case statements, you're gonna have those chunks of code in areas of memory with like hard addresses, right? So with absolute, like you won't know until you compile where exactly that address is, but once it does that, like in your assembly code, you're saying jump to this chunk of the code, and it could just do that.
So I mean, that's actually, what you're describing is control flow. Where do we want to update the instruction pointer to go after some control flow? Like a switch case statement actually is control flow. But what I'm saying is, can you think of an example where we want to access data at an absolute address from compile time? Yeah?
Global variables are stored in the text section below, or where everything else is, that's not going to change. So we have
Yeah, so if we have some sort of global variables that we want to access that, like you said, are stored in, for example, the text section, just constants maybe, we can program those in. What about memory mapped data? So in existing systems, what we typically have when we're dealing with different types of devices is we'll map some of their internal data, like registers or maybe buffers, to, like in your video card, we might map a frame buffer into some certain space in memory. In that case, we might actually be able to do some sort of absolute addressing mode in order to access that data. If, for example, let's say I told you that for your graphics driver, there's going to be a bit at this exact memory location that controls whether you want to render things in this quality versus that quality, whether you want to enable some sort of stage in your OpenGL rendering system or disable that stage. You could use memory mapped I/O to sort of perform that type of communication between devices, and those might have absolute addresses. OK. So one that we also didn't talk about was the based addressing mode. Can you think of an example where based would actually be useful? Any ideas?
Accessing something off the stack.
Yeah. So if you know where your current stack frame is, and you just, for notational cases, you want to keep things simple and say, offset 1 from the stack is argument 1. Offset 2 is argument 2, 3, 4, et cetera. You could use something like the based addressing mode. Yeah, exactly. Cool. So those are addressing modes. There's a lot more. No need to be super familiar with all of them. Just understand the key features of them and how they're used. Good. So what else do we have? OK, so we also had, so in terms of that question, these were basically the key concepts to go over. The next question, I'm just going to kind of breeze through, because it should be pretty straightforward. What we asked you to do was, for a given size of memory, for a given access granularity, like addressability, bits, bytes, megabytes, something like that, we asked you how many bits do you need in an address to represent, how many bits do you need to represent a memory address? And I'll just sketch the way that you would go about solving this for one of the modes. And unless you have any questions, then we can kind of move on. So basically, let's look at the question. What we asked you was, we have 64 megabytes of storage in a system. OK, that's our maximum memory size. We'll never need more than 64 megabytes. Figure out the number of bits required to address a particular location if, for example, the ISA is bit addressable. So what does that mean? That means that in this ISA, within those 64 megabytes, we can access any bit. I can say load the third bit, the bit at offset 3 in my 64 megabyte range. That's a lot of addresses, right? Intuitively, you can see how the smaller the granularity, the more number of bits of information you're going to need to use to precisely locate where that data is stored. Let's take a look at the bit addressable example. So this is for problem 5. We're just going to look at the first part and you can figure out the rest. But one of the first things to look at for this problem is just answering the question of how many bits are there total in, say, let's just look at 1 megabyte, for example. Let's take 1 megabyte, look at how many bits are in there. So in 1 megabyte, we have 2 to the 23 bits. OK. See Google Calculator for answer. No, you can literally just plug this into Google, right? And it'll give you this value. And you can figure out what the exponent is to figure out the number of bits needed to represent that value of bits in 1 megabyte. And it's straightforward from there, right? Because we know how many megabytes we have total. We have 64 megabytes. And we can just add these exponents together. And we can figure out how many, this is from 64 megabytes. We can figure out how many bits we need to represent an address in this type of machine. A lot of bits, right? 29. Think about the MIPS ISA. We have 32 bits in an instruction. Probably, and way more than 64 megabytes of data, by the way. Probably don't want to use an addressing scheme that's bit addressable. I want to use something larger. Maybe the word granularity makes more sense in that case. OK, and the other problems, or the other portions of this problem, you can figure out how to derive those. We're basically just changing the number of data access-sized elements in a megabyte, or in the memory. OK. Good. And then we asked you to implement a function that sort of deals with nibbles in MIPS, just to get you thinking about how do you access. So in an ISA that only lets you address data in this granularity, you can still kind of emulate the operations of an addressing mode that lets you access and modify individual bits, right? You just, as you saw in Lab 2, in fact, you have to mask data. You have to shift data when you're loading and storing it. But it's certainly possible. Maybe it takes more computation, though, than a system that is built for addressing those smaller granularities. OK. The next question was on the microarchitecture versus the ISA. Here we asked you to consider some of the trade-offs between those different levels of sort of the big stack of things, starting from algorithms all the way down to electrons, right? So we asked you some of those trade-offs. I'm not really going to go over those because I think they're pretty straightforward. Does anybody have any questions on the role of the microarchitecture versus the role of the ISA, where the divide is? No? OK, that's good, because it's pretty straightforward, I guess. I don't know, a couple of interesting things just to note about those levels of the stack. So we asked you a couple of things. What were they? Like we we asked you to look at, figure out like, if the machine does not have a subtract instruction, is that a property of the microarchitecture or ISA? Okay. I think those are relatively straightforward. Here's some things that I think are a little bit more blurry, that are also kind of interesting to discuss. What about if we have a machine that does binary translation? Remember Transmeta? Remember the company that took Intel x86 binaries and dynamically translated them into their own internal VLIW, which we've learned very long instruction word format. What about something like binary translation? Is that microarchitecture? Is that ISA? Are there examples where it crosses the boundary between the two? What do you think? Yeah?
I mean, I certainly wouldn't classify it as ISA because it's below the, if it takes completed x86, then it's not programmer visible.
Yeah, so from the perspective that it acts as an interface between one ISA and another, it's basically programmer invisible. Could you think of, are there any reasons why you might want to actually expose some of the translation, the binary translation elements to the programmer to improve performance? Can you think of any examples where you might want to do that? Yeah.
Not a specific example, but if certain instructions that in x86 are really fast, take a long time in VLIW, then you would go and tell them not to use those instructions.
So maybe, yeah, maybe on your system, on your Transmeta system, maybe you actually want to compile it to Transmeta because you think you can do a better job than the Transmeta hardware, let's say, translator. Maybe you actually have a native Transmeta VLIW compiler, and you want to say, for this binary program, don't do translation. I already have a really tuned copy of it that I spent a lot of time and effort making go fast. Yeah, that makes sense. What if, yeah, and that kind of ties back to the idea of maybe you're just doing the translation for backward compatibility with different ISAs. Maybe you don't want to do that always. You want to be able to tune when your system uses it and not. Maybe you want the kernel to use the native VLIW, but user programs to use x86. OK, that's good.
I have a question about using that. So like ARM, if you want to use the ARM ISA, you license it from ARM, right? And then I don't know exactly what the specifics are with AMD, but I think they would protect it, right? Because if it was only Intel, they'd have a monopoly. So wouldn't at some point Intel would have come after Transmeta? Even though they like how were they could they have gotten away with that, or?
So think about it though. What's Transmeta doing? What is their business model? What they're doing is they're saying we're going to use the Intel ISA specification. Remember the huge PDF files that we posted on the wiki? I don't know if you've looked at those, but what Transmeta is doing is saying we're going to look through those. We're going to implement your ISA. We're going to implement the abstraction of providing support for your ISA. But underneath, what we're doing is like the secret sauce. It's our own Transmeta magic, where we take an x86 program, like you've publicly specified, move things around, translate them into these VLIW instructions, repackage everything, and then execute that on our super efficient microarchitecture. So what they're doing is they're just using public information that any compiler designer would actually use to implement an x86 compiler, but instead of using it at the software level to do compilation, they're using it at the hardware level to do translation between x86 binaries and whatever internal form they want to use. It's like AMD, right? AMD does this too. AMD sells processors that run x86 or x86 with 64-bit extensions. But internally, they don't have Intel's microarchitecture. That's like super top secret stuff, right? What they actually do is they have their own microoperations. Remember the UOPs? They translate x86 instructions into their own microoperations and execute it on their own microarchitecture that they believe is hopefully more efficient than Intel's. So that's really what's going on here.
But I mean, like Qualcomm has to license the ARM ISA, but they do their own microarchitecture.
So I think what ARM actually does is that you can license what's called their IP, the actual intellectual property of how they design some of their systems.
You can do that, or you can also do the ISA. Maybe I'm not, I'm generalizing something about, but like TI, for instance, or like NVIDIA will largely do the IP, like ARM has their design core, and then they implement that and do some tweaks. But it's my understanding that Qualcomm says, okay, we're going to match your ISA, but we're doing our own core from scratch.
Does anybody know if?
Yeah, Qualcomm, they I think they did buy rights to the IP.
Okay.
But I don't think they actually changed the ARM microarchitecture.
But do you have to pay money if you use the ARM ISA?
What Qualcomm is doing is they've licensed, you can license hard IP that's netlist,
Yes.
or you can license synthesizable RTL. And so some of these people have licensed an IP core block, and they just drop it onto their K out. And what Qualcomm has done is they've licensed the Verilog and played with it.
Right.
And then sent it to data.
Okay, so I think it's going back to if it seems like for ARM at least, ARM provides different levels of synthesized versions of their cores that you can play around with, or maybe you just want to fabricate. But if you wanted to do, let's say, dynamic translation between ARM and your own ISA, I think that I don't think that you would have to pay rights to ARM or something like that. Yeah. Good question, though. Any other thoughts on dynamic translation? It's kind of interesting. It's kind of interesting. Bit of a side note, though. So Transmeta, actually, a lot of Transmeta doesn't exist anymore, but a lot of the engineers that worked on Transmeta actually work for Intel now, which is interesting because Intel does dynamic translation, right? They have virtualization functions. Maybe a lot of the translation that Transmeta did in hardware could be really useful for decoding complex Intel instructions as well. So there's things that can be learned in that space. OK, and just another thing that is kind of an interesting thought experiment. Remember open microcode? Remember John Cox's idea, which was basically saying, we're going to have a compiler that takes a C program and generates the same control signals that you implemented in Lab 2. So instead of having a decode unit, the next thing you fetch is like 16 bits, and those 16 bits are the control signals for your Lab 2. That's called open microcode. Where does that lie? Where does that sort of architecture lie between microarchitecture and ISA, if you had to take a guess?
It exposes your entire microarchitecture as the ISA.
Yeah, so open microcode basically says the microarchitecture, to a certain extent, is the ISA. Here is our microarchitecture. Here are all the signals. Now go and implement how you want to use those signals in a compiler. So that's a case where, remember the semantic gap? Remember the distance between high-level languages and the actual way that those are implemented in the hardware? That's an example where the semantic gap could be potentially very, very large, right? Very, very large. Because you're taking a C program, printf, and turning it in a C statement, printf, and turning it into zeros and ones that assert different wires in your system. OK, so that's microarchitecture versus ISA. The last question was the single cycle processor data path. You should be familiar with this from Lab 2 because you basically implemented the same thing in your own labs. So I'm not going to go through that question. If you have any questions on things that I didn't cover, please feel free to go to the TA's office hours or the lab sessions. For those of you who, and that's basically homework 2. For those of you that arrived a bit late, I have feedback forms. If you haven't filled one out, please, please, please fill one out. Give it back to us. We really take this feedback to heart, and Professor Mutlu will probably go over some of the common themes and his thoughts on how to address those. That's that. Any questions for me on the homework, on the lab? General-ish questions. For specifics, we can talk in office hours or the lab sessions. But any more general questions? Okay, reminder, the first exam is in like a couple of weeks, right? Huh? That's like 2 weeks, right? It's going to come quickly, so start preparing for that. And budget your time wisely between labs, preparation for the exam, homework assignments. Yeah?
Is the scope of material essentially like anything covered in lectures fair game?
Anything covered in lectures is fair game, and probably the required readings is also fair game, not the recommended readings or supplemental materials. Yes?
Is homework 4 going to be out and due before the test and before break?
Let's play by ear let's play that by ear in terms of homework 4. We'll kind of gauge as it gets a little bit closer when the exact due date will be.
Okay.
Yeah. We'll try not to overburden you because really you should be focusing on the lab assignment and the exams. Okay? Great. Thanks everyone. I'll see you on Monday.